Hi, my name is Yana, and I'm actually not a member in this team. The team member Yuzhou can't arrive here because of his visa problem, so I'm here. Their team has 3 groups, and they are Hangzhou Dianzi University in China, and the University of Sydney, Australia, and the University of North Carolina at Charlotte in USA. And the VQA problem is actually a challenge because it needs accurate understanding for both the image content and the question intention. And it has some important key components such as the fine-grained feature representation for the image and the multimodal feature fusion model and the answer prediction model. And from extensive experiments, we observed that the multimodal feature fusion model is actually very important in VQA problems. So, the current multimodal feature fusion can be divided to 2 different categories. And one is a first-order linear pooling model, such as the feature concatenation and feature summation. And but their performance is a little bit unsatisfactory. And the second is the second-order bilinear pooling model. And they are currently the state-of-the-art methods in VQA. And MCB model is a champion of VQA Challenge 2016. And it is very effective and converge very fast. But it needs high-dimensional output feature to guarantee a good performance. And the MLB model has a slightly better performance than MCB. And it has compact output feature, but it can converge a little slowly. And considering the merits and the drawbacks of these 2 models, we propose our multi-model factorized bilinear pooling method, which can enjoy both the merits of fast convergence and the compact output feature. And we also extend the MFB model to a higher-order pooling method, which can learn some complex interactions among feature dimensions in multimodal data. And the idea of MFB model is actually inspired from the factorized machine and the recent factorized bilinear pooling method for unimodal data. And the method is actually very simple to implement because it has only off-the-shelf layers, such as a fully connected layer, the sum pooling layer, and the element-wise product layer, and the feature normalization layers. And the MFH model is actually consisted of several cascaded MFB blocks, and the output feature of MFB block can be concatenated to form the output feature for the MFH model. And in this work, we also did a little modification to the original MFB model, and we split the MFB model to the expand and the squeeze stage. And the output feature of the dropout layer of the current MFB model are fed to the next MFB block to perform a 3-way element-wise product with the feature X and the feature Y. And this is a network architecture, and this work is actually inspired from the MCB model. And we additionally add question attention to this network to make it learn some keywords in the question in a self-attentive way. And these are results on the VQA dataset. From these results, we can see when we're using 7 MFB models, we can achieve about 68 accuracy, and when we use 7 MFH model, and the performance is a little bit better. And on the VQA Challenge 2017, we use 9 MFH model, and we achieve about 68 accuracy on the test standard set. And also the code and the best single model have been released at GitHub. And that's it. Thank you for your attention.
Thank you so much.
So if you have any questions, you can contact the author, because I'm not familiar with his work.
Thank you. By the way, I would like to mention that we just made all the leaderboards for all the different accuracies public. So teams can go on visualqa.org and can check their test challenge accuracies, which was not public yet. So now I would like to invite the team, other team at second position, and the team. So this is DLAIT team. The team members are Youngchul Son, Kibam Lee, Chong Ryo Lee, Gyu Tae Park from Samsung Electronics, and Jong Ryo Lee will be giving the talk.
Hello, this is Team Delight. It's been an honor to be here as the challenge runner-up. My team members are Youngchul Son, Hibom Lee, Jongyu Lee, and Gyu Tae Park. I'm Jongyu Lee, and I'm from Samsung Electronics. Before starting, please understand that due to the short notice, we didn't enough time to prepare many techniques used for this challenge. So there are some missing details in this material. Nevertheless, it still contains the key idea of improving our models in terms of accuracy with the largest margin. And that idea was proposed by Youngchul Son. And let's get started. The title is Visual Question Answering with Supervised Attention. Let's see this example. This is a typical example of the visual VK problem. The question is there a man taking a photo? So, and on the right side, there are two attention regions, which are generated by a VK model with visual attention. So obviously, the better attention regions is better for the model to predict the correct answer. So we believe that accurate attention results is needed for predicting the correct answer. So motivated by this, we propose a supervised visual attention approach to increase models' attention accuracy. So let me explain how we implement this idea. So suppose that we have a VK model with some VK model with visual attention, and such a model usually takes image features from the image and text features from the question. And by combining them, it computes the attention map for visual attention. And suppose that we have some attention ground truth for this QA pair. So then we can compute the difference between machine-generated attention map and the attention ground truth with KL divergence. And the result of KL divergence becomes the second loss. And the first loss is obviously the cross entropy over the answer classification of the VK model. And in this way, we can train the model with the visual attention supervision. And then one can ask about how we can obtain ground truth for attention regions. Unfortunately, it is costly to annotate region ground truth on the existing VK data set, so we consider a simpler way. So we automatically generate region annotated QA data set by utilizing region descriptions from the visual genome data set. In the visual genome data set, for each image, there are multiple bounding boxes, and for each bounding box, there is the corresponding region descriptions. For example, there is blue bounding box, and there is the corresponding region descriptions. Person sitting down in white shirts, red shorts. From this description, we can make a question. Is there a question? So is there a person sitting down or white shirts, red shorts? The answer is, of course, yes. And that blue bounding box can be used as an attention ground truth. So in this way, we construct the region annotated QA data set from the visual genome data set, and the generated data set is called the IQA data set. And this is result on the original VK data set for our approach. We want to see some positive correlation between attention accuracy and the VK score. The attention accuracy is measured with the attention score, and the attention score is defined as the sum of machine-generated attention weights for the ground truth regions. And the attention scores are measured by averaged over 1,000 samples of the visual genome QA data set, and those samples have hand-annotated ground truth regions. So the results are represented in this figure, and in this figure there are 4 categories. 4 categories over different image features and the use of visual genome QA data set. And for each category, there are corresponding 3 points. For example, let's say the top 3 points. They are included in the last category, and the last category represents that we use the legendary image features, and also we use the visual genome QA data set, which is different from the IQA data set. And among these 3 points, the lowest one is the result without the IQA data set and attention supervision. And the highest one is the IQA data set and the attention supervision. So we can see that the difference between the highest one and the lowest one is almost 1 point. So that is, we can enjoy the extra 1 point with our approach. Almost 1 point. And here are qualitative results. Let's see the above example. The question is, what color is the stapler? The stapler is there, and the color is red. And there are 2 attention results. And the right one is the result with supervised attention. And in this result, the model successfully focused on the stapler, and it answers correctly, red, with high attention score. And this is our short report for this challenge. We use different baseline VK models. The first one is multimodal attention network, which is a variation of dynamic memory network. And this model was used by us in the VK challenge 2016. And the second one is, and this model incorporates visual attention and textual attention. And second model is low-rank bilinear pooling-based model. Actually, this model is not the same as MLB. It is much simpler model, and it was made for demonstrating the generality of our approach. And for this challenge, we use 2 kinds of legendary image features, and we use the visual genome QA data set and the IQA data set as additional training data set. And also we use the train split and validation split of the VK set as the train set together. And there are 2 tables. The above one is about the single model accuracy. So our best single model accuracy is the 65.4, and the below table is about our final accuracy with 12 model weights ensemble. So you can check our points. In conclusion, we propose the IQA data set, which is generated from the visual genome region descriptions. And also we propose on the supervised visual attention approach to increase models' attention accuracy. And we show that our approach successfully improves our models in terms of VK accuracy. And thank you to the VK organizers for the workshop and challenge and this nice data. Thank you.
question?
So you have trained this on this region annotated data and just applied it to VQA, and then basically you kind of fine-tune it for VQA. Do you observe that it still remembers what it has learned to attend to the right regions? Have you looked at this final attention predictions, or it forgets that and just sort of gets fitted to VQA? What's your impression?
I'm not sure I understand that question. In fact, we trained our model from scratch with the VK data set and the IK data set together. So there's no fine tuning.
Oh, okay. Jointly trained
Yeah.
on both data.
Yeah.
Okay. But still, like, is there attention on the VQA data? Have you looked at it? Is it able
So in fact, the VK data set doesn't have the region ground truth. So in that case, the second loss becomes 0. So in this way, we jointly train with 2 data sets.
Questions? Okay, so now I would like to invite the winner team to present their talk. And the team is Adelaide Tini ACRV MSR team. The team members are Damon Tini, Peter Anderson, David Golub, Posen Huang, Lee Zhang, Xiaodong He, and Anton van de Hengel. And Damon and Peter will be presenting the talk.
All right, thanks everybody for coming here. So I'm going to present our model. We got the first place in the challenge. And this model is a combination of 2 things. It's on one side a pretty simple neural network, and on the other side some novel image features that my colleague Peter will present after mine. So we have a pretty simple model here, a straightforward approach with a joint embedding. So on one side you have the image, on the other you have the question. Embedded with a CNN and recurrent network on both sides. And we have attention over the image. It's a pretty simple model as well, just a single head question-guided attention over the image. Then you have combination with simple multiplicative element-wise multiplication. And as in most models, well, most successful model, it's all about the details. So we have a few key points that make the performance significantly better than a baseline. We have, well, like I mentioned, those new image features, but you have also some gated activation on all the nonlinear layers. We also use an output that is a regression over output over answer scores instead of classification over candidate answers. And we also initialize the classifiers at the end with some pre-trained representation of the answers. So I'm going to go into more details about all of these points now. So as I said, all the nonlinear layers are using gated activations. So this works as follows. You have first a computation of activation with a hyperbolic tangent. So this uses the first set of linear weights. Then on the other side, you have computation of a sigmoid, of a gate with a sigmoid. So that uses another set of weights. And then you combine the two with just a multiplication. And this is very similar to what you see in recurrent units like LSTMs or GRUs. And in our case, that shows that it was bringing some pretty big improvements over ReLUs or even hyperbolic tangent activations or even combinations of residual layers and pretty much whatever you can imagine. And we don't come any novelty on this. This is actually a special case of the highway networks, and this has been used previously in other works, especially in NLP. Now on the question side, it's pretty simple as well. We have we use pre-trained word embeddings, the global vectors. Then we have a GRU, and it's a simple one-layer forward GRU. We have tried other more clever, supposedly more clever options like multiple layers, bidirectional GRUs, and things like that. And none of those was improving the result. So we're going to have a report that does an extensive comparison of the results of all those options that we have tried. And what is interesting to note is that in some cases, simple is actually good enough, or even just the best. Then for the attention over the image, it's a simple model as well. Like I said, a simple one-head, one-pass attention over the feature map. What's more interesting is on the output stage. So here, instead of doing a classification over a set of candidate answers, we have a sigmoid at the end of the network that does a prediction of the score on the answers. So as you know, in the VQA data set, you have scores for the ground truth answers that go, well, most of them are 0 or 1 for the correct or incorrect answers, but some of them have scores between 0 and 1 whenever the annotators disagreed. And you might have also some questions that have multiple answers with the ground truth score equal to 1. So with this approach here, you can use the signal from multiple answers for one question, and you can use also the uncertainty that is in the ground truth score. Then one more thing that we do on the output stage is that the last layer, which is a linear layer that does the classification over the candidate answers, while the regression over the scores of candidate answers, we pre-train this, we initialize this layer with a pre-trained representation of the answers. So basically this last matrix W that you see down here is actually computing a dot product between the final representation that is computed by your network and the representation of the answers that is learned within the network. So each row of this matrix basically encodes the representation of the candidate answers. And we can use some prior to initialize this matrix with some representation of those answers. And we have two strategies to do that. So in some cases, it's useful to use whatever the text represents. We use then the glove vectors, the glove word embeddings, to initialize the rows of this matrix. And on the other side, we use visual information. And to do that, we look up some exemplar images from Google Images with whatever the answer is. And we get some CNN features from those images. And that serves as a prior on the representation, while a prior on the space of representation of the candidate answers. Now a few practical details. So concerning training, we use, obviously the VQA-V2 training set. We also use some additional data from the visual genome, which also has some question and answers. And we only use the questions which actually overlap, whose answer overlaps the candidate answers that we have identified on the VQA-V2 dataset. And we also use only the questions whose images are actually used in the VQA-V2 dataset as well. Now for the training itself, when we train the network, we make sure in the shuffling of the training examples to keep the balanced questions in the same mini batches. And we found that to be a little bit helpful. I think my intuition is that when you have balanced questions, you have, you have two different images that are kind of pulling the gradient, pulling the weights of your network in two different directions. And we found that keeping them in the same mini batches was improving the result. And then to get the best result, we get use an ensemble. It's a pretty big ensemble of 30 networks. But it's interesting that with just a couple of networks, or even 5 of them, we get a very good improvement. And up until 30, it seems that it was helping. We didn't go any further.
So now I'll talk a little bit more about the image features that we use, or if you like, the front end of this model. So this is some work that we're quite excited about for a couple of reasons. One is that it works equally well for VQA and image captioning, so it's sort of nice to have that validation. Secondly, the relative improvements are quite significant. So if you're looking at cider or spice or VQA scores, improvements are about 6 to 8%. And the actual intuition behind this idea is it actually makes sense and it makes the model more interpretable, which is a nice thing to have. So the main idea here is that we calculate attention over objects and other salient regions in the image. So this is in comparison to the more usual approach illustrated on the left-hand side, where attention is taken by weighting the features in the spatial output layer of a CNN. In that case, each feature corresponds to an equally sized image region, which is sort of arbitrarily laid in a grid. So in our approach, we, in a bottom-up fashion, hence the bottom-up attention name, we look at features for these salient regions, and for each of these regions, we have a feature vector that can be used then in any follow-on model really as a drop-in replacement for CNN features. So for the implementation for this, we use faster RCNN, which could be seen really as a bottom-up attention model. We train this on visual genome, so we do quite extensive cleaning up of the data, and we end up with about 1,600 object classes, and we also predict 400 attribute classes. So the pictures there, they'll be possibly hard to see down the back. The idea is just to give some intuition for the quality of these features and the regions. If you can't see, for example, on the left-hand side, it identifies a smiling man with a black jacket, the red bridge in the background and the water, and his hands, his blue jeans, etc., etc. So the quality of this information is really quite good. But for all downstream tasks, we throw away the labels and we just use the features. So the feature that we use is the mean pooled feature in each spatial region from the final output layer of the faster RCNN. So to give some idea of the qualitative differences in how this attention model now works, so the question at the top is the person wearing a helmet. In the middle at the top you have a ResNet baseline, and then on the right is this approach. And so you can see that the ResNet model sometimes has these sort of spurious focus areas like in the top left. On the right-hand side, there's a very small red box around the helmet, which is actually the most tightly cropped region with the most attention, and there's a little bit more context of the face around that. Similarly, in the bottom example, what foot is in front of the other foot. This here, the ResNet does poorly. I suspect in this case it's the features that are primarily the difference. So being trained on ImageNet, it really has probably not much knowledge of things like feet and shoes, where the visual genome data set is more diverse, and so we get a really nice crop around the 2 feet, which would be useful for answering the question, but in actual fact our model still gets this wrong. But nevertheless, if we look at some more failure cases, our model is not a very good student. It's not particularly good at counting or reading, but it's nice to see that we are at least looking in the right place in terms of counting the oranges. And in the bottom, if you can't see from the back, there's some text in the top right-hand corner, which is nicely cropped out. So the attention models are probably getting good enough that you might actually be able to use this as input then to some more specialized processing modules that can read and count. So I mentioned this works for captioning. I won't dwell on this. It's a captioning example. We're interested in cases where language priors steer us in the wrong direction. That's one of the big themes. This is a difficult image because it contains a couch in a bathroom, which is pretty out of context. The ResNet baseline incorrectly identifies this as a toilet. The full model, which we're calling up-down because it has attention in both directions. The main reason it improves is because in the bottom row, second from the left, there's an image region that encompasses both the couch and the man, and so this region can be queried to basically get the answer for what the man's sitting on. And so it's very important that you have both small and large attention regions, and in our approach you no longer have that trade-off of trying to find the right size that you have in the ResNet approach. So we mentioned it works for captioning, so we're actually also at the top of the captioning leaderboard, at least in almost all metrics, although of course this is very competitive. There's a couple of metrics where the 10-cent AI team is beating us. Down the bottom in blue is, that's actually the self-critical sequence training work that was presented earlier in the conference. It's a very nice piece of work. So it's good to see, I guess, that we're already making significant improvements, although I actually think their optimization of the metrics is much better than ours. You know, hopefully our work is complementary to others. And again, on a ResNet baseline, the improvement's about 6 to 8% on well, it's 8% on CIDR, 6% on SPICE. We have an archive paper. I'll put the link up again at the end.
So in terms of results on the VQA, the result that we have now for our best model is above 70%, so it's after tweaking a few more hyperparameters since the end of the challenge. Now, the interesting comparison is that we can run the exact same model with just the standard ResNet features. That's what we have in the table here. So the number is lower because it's just a single network, not an ensemble. And it's also evaluated on the validation set, which is just obviously not used for training then. And you can see that the improvement is very large. So a relative improvement of about 6% versus the ResNet features. So, and this is just as simple as swapping the original standard ResNet features with those that we just presented. Now, a few takeaways and some conclusions. So what we found during the development of this model was that it's very hard to make predictions on what's going to work, what's not going to work, and how the improvements, how big, well, how large the improvements are going to be. So we found it to be, well, it's really crucial to have something that you can train quickly and experiment quickly with. And unfortunately, it's hard to make experiments with smaller training sets and with smaller models because very often the results will not pan out with your full-blown model or with just the full training set. And I guess the biggest takeaway that you can remember here is that there's still a lot to be gained with the better image features, especially with those that we presented here. And we're going to make those available so that we can, well, you can use them in your own models and see how much it improves then. So as Peter said, there's already a paper in archive that details the bottom-up image features for captioning and VQA. And there's going to be another paper pretty soon with a lot of experiments and comparison between the different choices that we had to make in architecture, hyperparameters, and so on. And if you have any question, you can ask now or come to us later in the afternoon during the poster session. Thanks.
Questions?
Hi, very impressive work. So I have a question, like in your fine-tune, further version, like the 7x7 map actually got better than 14x14 map, right? So like usually like for VQA, people thinking that it's more like there's more like fine-grained clues, and so people like generally resize their map. So like why 7x7 is outperform by 4? Yeah. So have any reasons?
Well, it's hard to say. I don't have a good explanation on why it's better with a coarser feature map.
Like, is this because it's easier to optimize, or like some other reasons you think, or specifically architecture or something?
So quite frankly, the initial choice of 7x7 feature map was just for having a model that's much faster to train, and well, in the end, it ended up being a good choice performance-wise. But I don't have a good explanation. It might be because well, the coarser map maybe match better the sizes of objects in the images. It's really hard to say.
I have, sorry, one comment. It's more of an idea, but if when you need to identify which features belong to the same object, there's a sort of a feature binding problem, or you need to find the relation between objects you really need an attention region that captures both. And I think the man sitting and the couch is that example, because you're doing a content-based lookup for the man, which is the context information that you have. You need a region that returns couch, so it has to contain couch and man. And if the regions are very small, that's not possible, so hence this trade-off.
More questions?
This is just a quick one, but I'm just curious, how much did not having the sort of 0-1, not having the softmax and actually looking at the softer accuracies of each answer, how much did that help?
So there are two things. It's softmax versus having a sigmoid as output. That's a very big improvement. It's the order of, well, don't quote me directly, but it's like 4%, something like that. And soft scores, instead of just keeping 0 and 1s, it's maybe 0.5% or 1%, something like that.
So I really like the semantic, the bottom-up attention stuff. Is there a, maybe I missed this, but is there a way to generate new boxes based on the words that are mentioned in the question, if you haven't had them covered?
Yeah, so not in our current implementation. So basically everything's pre-trained and fixed, much the same way that you pre-train on ImageNet. So the boxes, I didn't mention details, but basically we have a threshold of confidence of object detection that then selects a number of boxes. We actually allow that to vary between images, so there's different numbers of boxes, but that's not super critical. But yeah, I think you know, there's probably nice, interesting ways to think about doing more end-to-end learning with this. So.
Yeah, and so the number of boxes that are kept, so like Peter said, it's pre-trained, but we have on average, I think, maybe 60, something like 60 object regions per image, which is probably a high recall, and the further attention standard mechanism can then, I guess, select which ones are the more accurate. That's just an intuition.
Let's thank the speaker again.